So here we talk about derivatives of exponential and logarithm functions. Starting with our favorite derivative, the derivative of e to the x is just e to the x. Then from there, we can use that to figure out what is the derivative of a to the x, where a is anything, not necessarily the e. So we can do this by first converting a to the x into e to the natural log of a raised to the x power. So if you remember, e to the natural log of a, e and natural log are inverses. That's going to cancel each other out and give you the a to the x that we have to start with. So then we can say this is like taking the derivative of, and now we can use our properties of exponents. E to the natural log of a to the x is e to the, and then we multiply those together, and I'll write the x in front. So it's e to the x natural log a. Now we know our chain rule for derivatives. The derivative of e to the u is going to be e to the u du. So we get that same exponential back, e to the natural log of a, times the derivative of the constant natural log a times x, which is the natural log of a. Remember, this e to the x to the natural log of a was just our a to the x in disguise, and so we get that the derivative of a to the x is a to the x natural log a, which means then our chain rule as applied to an exponential of any base is a to the u natural log of a times du, in whichever order we want to do the natural log a and the du. So for example, if we wanted to find the derivative of e to the x squared plus 5x, we would get e to the u, that same exponential, times du, the derivative of the exponent, which would be 2x plus 5. Granted, that's not pretty, but it's still nicer than, say, taking the derivative of maybe 7 raised to the cosine x, which will be the same exponential back, just like we did with e, but now we have to add in this annoying natural log of 7, and then times the derivative of cosine of x, which is negative sine of x. So even more irritating. So let's talk about the derivative of natural log of x. So we remember what it is, but let's see where it comes from a little bit. So if we start out with our function y equals natural log of x, and then we exponentiate both sides, that will get us to e to the y, and remember e to the natural log of x, because e, the number, Euler's number, raised to the logarithm base Euler's number, those are inverses, and we'll just get x. Now if we differentiate that using implicit differentiation, we'll get e to the y times y prime is going to equal the derivative on the other side of x, which is 1. And so that will get us to, instead of making that an equal sign, let me make it just an arrow. So we're going to get y prime is equal to 1 over e to the y. But remember, y we said was natural log x. And here we are again with e to the natural log x is going to be just x. So there we have it. The derivative of natural log x is 1 over x. And that means the chain rule as applied to a logarithm, you can either call it 1 over u du, or some people prefer the du over u. Those are interchangeable. So the key is to remember that when you're going to take the derivative of some crazy logarithm, use your properties of logarithms first. So use properties of logs first. So for example, if we are going to find the derivative of, say, the natural log of, let's say, the fourth root of x to the third times x minus 2 cubed, say all, whoops, lost my pen, all over maybe the cube root of 3x minus 2. Holy smokes. Instead of jumping in and doing all kinds of craziness with the calculus, let's first break this up as much as we possibly can. So we know the log of a quotient is the difference of the logarithms. So that's going to be the log of the numerator, which I'm going to write as x to the third times x minus 2. I don't really want to make those both 3. I'm going to change that second one just because I can to a 2. And then that is going to be all raised to the 1/4 power. Oops, sorry, that's going to be in the logarithm there. To the 1/4 power. And then minus the log, the natural log of, and we'll write that as 3x minus 2 to the 1/3 power. So then what we can do is start using more properties of logarithms. So we can bring this exponent in front and call that 1/4 of, and if you're okay, I'm going to start doing this quicker. The log of a product is the sum of the logs, so that's going to be the natural log of x to the third plus the natural log of x minus 2 to the second. Close that parentheses, minus, we have 1/3 times the natural log, on the very clear 1/3, 1/3 natural log of 3x minus 2. And then we can, let's see, if we bring this up, I'm going to try to give myself a little space here. So now we can try to find eventually the derivative of, and we can now use more properties of logarithms. I'm going to bring this in front and distribute the 1/4 to call that 3/4 natural log x. And likewise, that is going to be 2/4, which is going to be 1/2 natural log of x minus 2. And then we're going to get, we just have this other, I think we've done all the simplification we can using our algebra skills. And so now we're finally ready to do some calculus. So we'll get 3/4 times 1 over x, which is going to be 3 over 4x. We'll get 1/2 times 1 over x minus 2, which is going to be 1 over 2 times x minus 2. We'll have a minus 1/3 over, now we're going to go 1 over, so we have the 3 from the 1/3. I better write this out. So we write that as 1/3, there's the 1/3, and then we want du over u, so that'll be a 3x minus 2 times the 3 from the derivative of 3x minus 2. We get a little bit of cancellation there. So at the end of this whole thing, we've got 3 over 4x plus 1 over, and you can distribute or not, and then we'll have a 1 over 3x minus 2. There was our derivative of a massive logarithm. So I think let me do one more thing. I'm going to go to a new screen. I just want to make a point that we cannot gain domain by differentiating. We cannot gain domain by differentiating. And in fact, sometimes we may even lose a little bit, but we can't ever gain any. So for example of that, let's say we have f of x is equal to the natural log of x plus 3. So we take its derivative and we get 1 over x plus 3, and then times the derivative of x plus 3, which is just 1. So if we ask what is the domain of this derivative, then at first glance, we might say, well, the only issue is you can't get a 0 in the denominator, so you might think incorrectly that the domain would be everything except for -3. This is not true, because remember, this came from this function, and our domain in the original, because that's in a logarithm, that could only be values of x that make our logarithm strictly greater than 0. So that means we had only x greater than -3. So here then we can't gain all of those values, although we can't gain more values. So we couldn't use -3 in the original function. That is still excluded here, but we can't somehow get all those numbers to the left of -3 like this might lead us to believe. So instead, our domain is still going to be x greater than -3. It remains what it was before in this case. Okay, very good.